Bam! Mr. Tarrou. In this video, we're going to be taking a look at number 2 from the 2018 Calculus AB Free Response Test. In the description of the video, you'll find a link to the PDF of all of these questions, a PDF of the marking scheme, a PDF of the master grader's scoring comments, so you can learn where students missed some easy points maybe, or the majority of the points, how the questions were misconstrued and such, and prepare yourself for doing as well as possible, getting a 5 hopefully on this AP test. You'll also find time descriptions, or time stamps, excuse me, to skip ahead to each of the 4 parts that make up this question. So it says, a particle moves along the x-axis with a velocity which is equal to 10 times the sine of 0.4 t squared over t squared minus t plus 3 for the time period, and it's a closed interval, from 0 to 3.5. The particle is at the position of x is equal to -5 at t is equal to 0. So we have an initial condition, an initial basically placement of this particle, which is going to come into play for part B and C and possibly D, I don't remember. But here in part A it says find the acceleration of the particle at t is equal to 3. Your textbook probably will say that as a standard letter, S of t is a description of position, V of t is a description of velocity, and A of t is a basically sort of your standard notation for an acceleration function. You do not want to introduce a new function name unless you tie it together with what you've done. The first derivative of position is velocity. The second derivative of position, or the first derivative of velocity, is your acceleration function. And that's all we have to do here. Since we're given a velocity function, we just really need to see what v prime of 3 is for the acceleration. And it is safest for you to simply write v prime of 3 is equal to, and that answer comes out to be negative 2.118. Don't forget, this is a calculator-based question. Do not try and take the derivative of the velocity function using the quotient rule and some kind of craziness, because you're going to need a calculator anyway. The answer is a decimal. Now we still need to write this in context of the problem, but it's kind of a weird one. It's not an application problem, so we don't know what the unit of measure is for time, and we don't know what the unit of measure is for position, like inches or feet or something like that. So I'm still going to write a summary statement in context of the problem, but it's not going to have any units of measure. By the way, if you write v prime of 3 equals a of 3, you know, just making sure it's clear in your head that we're talking about acceleration is equal to negative 2.118, that's fine. But if you just write a of 3 is equal to negative 2.118, you've just introduced a new function name again without describing or explaining where that came from, and they do not like that on the AP test. So if you're going to write a of 3, make sure you write that it's equal to first v prime of 3, though it's not necessary, and I actually recommend that you don't do that. So we have the acceleration of the particle at t is equal to 3 is equal to negative 2.118. Always round off to your third decimal place or your thousandths place, and also be specific about the time period. This is not a constant function. Its acceleration is going to be different at different values of t. Find the position of the particle at time is equal to 3. Find the position of the particle. Well, we have that particle's velocity. It's a rate of change, and if you integrate a rate of change, you get an amount of change. So we want to possibly, let's see here. Yes, we have its velocity, and we have its position at t is equal to -5. So we need to think about that net change theorem and use that initial position to then remember that, okay, well, at time 0, we're at -5, and then off of time 0, you're going to find out how much change there is between that time of 0 and that time of 3 and add it to this initial position. So your position at t is equal to 3 is going to be equal to where you were at t is equal to 0. Let me do this. Let me just say let s of t equal the integral of v of t dt. This is not necessarily in the marking scheme. As I glance down, you're basically they're just actually seemingly arbitrarily using a new function name, but I've seen in my years of teaching AP Calculus where that could bite you in the butt. So I'm going to define a new function as the integral of velocity, and thus it is position. Maybe overkill, but I want to make sure that we get as many points as possible. S of 3 is going to be equal to the position at t is equal to, oh, excuse me. Well, yeah, it is we do have a value of x. We could have called it x of t. Now it makes sense how they just sort of arbitrarily introduced that new variable nut function notation, but I'm going to say s of 0 plus, and now we're going to integrate the rate of change off of as a lower limit, the time at which we had that initial position, because that's where we start moving from. So 0 to 3. Okay, and I'm just going to put in this notation for v of t because it's actually a good idea with these, again, the calculator-based questions. We did this with question number 1, is to actually put this somewhere in your calculator, like a y sub 1 or a y sub 2 line, you know, where you go to type in your functions to graph so that you can just recall it from the memory instead of typing it over and over and over again. So we have s of 0 is equal to -5, and then plus that we're going to then type this into our calculator and get right off the top of my head, well, my work here just has a final answer, so let's type that in. Let me double check that. Excellent. And I went ahead and rounded off to the 4th decimal places. Now, we have our work shown. Probably going to get a point for setting up the correct equation and using the proper limits and take into account that we understand there's an initial position and stating that the position of the particle at t is equal to 3 is equal to -1.76. So here we go. Y equals alpha y equals, put in a fraction, and put in that 10 sign of 0.4x squared, close it up, and we have our denominator of x squared minus x plus 3. Okay, we're going to second quit this. I'm going to go to math, ask it to do a numerical derivative. That's with respect to x. And we just put that function into y sub 1. So alpha trace, select 1, and we want that derivative when x is equal to, or t is equal to 3. And that is where the negative 2.118 came from that we put on the board. So now with part B, since we were smart and have that, we have that velocity function stored, we're just going to put in -5 for that initial position. Plus, now instead of taking a numerical derivative, we're going to take a numerical integral, so that's choice 9. Well, as the software is in my calculator currently. Lower limit of 0, upper limit of 3, and we put that function, that velocity function, into y sub 1. Again, with respect to x for the integration. And there is our position of the particle at time of 3. Let's get on to part C right now. Part C, we're going to evaluate the definite integral of v of t dt and evaluate the definite integral of the absolute value of v of t dt and interpret the meaning of each integral in context of the problem. If you know how to use your calculator, then the only thing really that this question is testing, besides the fact that your teacher showed you how to use your graphing calculator, is do you know the difference between these two integrals? So let's go ahead and get this out of the way. We're going to set up the definite integral from 0 to 3.5 of v of t dt, and that is going to be equal to 2.844, or there's an optional answer of 0.845 depending on how you calculate your definite integral. In other words, you can find the value of this definite integral by first graphing the function and then using the numerical integration function with the graph, or just in the home screen. And then we have the definite integral from 0 to 3.5 times the absolute value of v of t dt. And that should usually be a different number. We're looking at 3.737. And here's the deal. When we're moving to the right, our velocity is positive. When we're moving to the left, our velocity is negative. And if I move to the right, let's say 4 feet, and then my velocity becomes negative, and I move back 3 feet, then I'm only 1 foot from where I started from. That's what you get when you integrate velocity. You get a change in position. You get I say sometimes you integrate a rate of change, you get an amount of change. Well, when we're talking about things moving, particles moving, that's called displacement. How far are you from where you started from? And if you went right 4 and back 3, you're only 1 foot away. So you can maybe it gets hidden just how much action may there have been. So when you integrate an absolute value, well then it's going to say, oh, you moved with a positive velocity 4 feet, and you moved backwards with a negative velocity, or left with a negative velocity. Well, we're going to go ahead and with that absolute value function make sure it still comes out to be positive, and so we see that whole distance, that total distance traveled. Displacement, total distance traveled when you're integrating a velocity function. So again, our conclusion here, or our interpretation, is that definite integral from 0 to 3 of v of t dt is the displacement of the particle over the time period of t being greater than or equal to 0 and less than or equal to 3.5. So between the time period of 0 and 3.5, we really don't know how far to the right or left that particle moved, but its final resting place, or its position, 3.5 seconds or units of time after 0, is a displacement of 2.844. So finally, its position right now is that far to the right from its initial position. The definite integral from 0 to 3.5 of the absolute value of v of t dt is that total distance that particle moved or traveled over the same closed interval time period between 0 and 3.5. So for part C, we want to find the definite integral between 0 and 3.5. So math, numerical integral, lower limit of 0, upper limit of 3.5, have that function stored in y sub 1 with an integration with respect to x, because that's all we can put in our calculator, at least, well, unless you're doing parametric functions. And we have that displacement for the, I want to say first 3.5 units of time period, but it's really between 0 and 3.5, and that came out to be our 2.844, because we should be rounding to the third decimal place correctly. Now, for finding the total distance traveled, again, math, choice 9 in this particular case where my software is, 3.5 for the upper limit. Now, for the absolute value, we're going to go to math, number, and select absolute value, and there's probably another way of finding that there. And the function, again, we have stored in the first position, again, alpha trace to pull up that menu, integrating at least how it's typed in the calculator with respect to x. And there is our total distance traveled, hopefully coming up right there. It takes a little bit longer for those absolute value integrals. Part 4, or D, coming up right now. Part D, in the last part of this question, a second particle moves along the x-axis with a position function x sub 2 of t is equal to t squared minus 1 for that same closed interval of t being between 0 and 3.5. At what time t are the two particles moving with the same velocity? Well, here we go from straight calculator work. There's just a little bit of calculus we do by hand, but again, just understanding that if we take a derivative of the position function, we get velocity. They're just making sure that we understand the relationship between position, velocity, and acceleration. So we just need to say, okay, well, x prime sub 2 of t is equal to 2t minus 1, and then we're going to, and remember, we should already have this typed in the calculator for y sub 1, so we can just keep recalling that memory location through the previous parts of the question. We're just going to type this into y sub 2, graph these two functions, find out where they intersect, and well, that's the answer. So that x prime sub 2 of t is equal to v of t when t is equal to, going to 3 decimal places, we've got, and actually they don't really want you to round until you get your final answer. So we're looking at something around 1.5705 dot 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 2 particles are moving with the same velocity. Remember, by the way, velocity takes into account the direction, with it being positive or negative, along with the rate of change, whereas speed, not that it's in this particular question, is the absolute value of velocity. And for good measure, I'm going to go ahead and put that closed interval on there. So the two particles are moving with the same velocity at t is equal to 1.57 on that closed interval where t is between 0 and 3.5. So how did we find that? How did I find that time period where those two velocities were equal? Well, thankfully, we already have the equation for the original function typed into our calculator, so I'm just going to come down here and type in the derivative for our second particle, which is 2t or x minus 1. And I'm going to go ahead and hit window, and it's already set up. We have that time period between 0 and 3.5, and I have no idea if we're going to see this on the calculator because these window settings from a previous question, and actually they're from question number 1 of the same AP test. And my steps are a little bit small for my calculator, so my calculator is running rather slow. Boom, so there's the intersection of our graphs. Second calc, ask for the intersection between the two functions. What's the first, what's the second? Guess, not too important here because it appears like there's only one. And there's our time period at which the two velocities are equal. That time is 1.57054. Hi, Mr. True. Bam! Go do your homework. So now with part B, since we were smart and have that, we have that velocity function stored, we're just going to put in -5 for that initial position. Plus, now instead of taking a numerical derivative, we're going to take a numerical integral, so that's choice 9. Well, as the software is in my calculator currently. Lower limit of 0, upper limit of 3, and we put that function, that velocity function, into y sub 1. Again, with respect to x for the integration. And there is our position of the particle at time of 3.